morning, student. In the last class, we have discussed about the magnetic field produced by a finite wire, and after that, we have approximated the magnetic field due to a infinite current carrying wire. Okay. In this class, what I am going to do, I am going to do a alternative definition of ampere. Okay. What is the definition of ampere? I is equal to, as you know, I is equal to dq by dt. Okay, so 1 ampere current means 1 coulomb charge 1 second. If 1 coulomb charges flow through a conductor for 1 second, this is known as a 1 ampere. So it's almost a almost a good definition of ampere, but it's not that practical because you cannot sometimes imagine what is 1 coulomb, how much time it is flowing. Okay, so this is a theoretical definition, but not much practical use. Okay, now we are going to define a very practical definition of ampere. Okay, and for that definition of ampere, we are going to use the earlier concept which I have already discussed, basically the magnetic field due to a infinite current carrying wire. Okay, suppose you put a infinite current carrying wire like this. Sorry. Okay, and the current is flowing through this wire along this direction. Okay, as I have already discussed, the magnetic lines of force around this wire will be like that. Symmetrically, they will be symmetrically distributed in the form of a circle. Therefore, if I plot the magnetic lines of force, it will be like this. Okay, it will be like this. These are magnetic lines of force. Okay, I mean I have used the dotted line so that it means the lines are encircling the wire. Okay, and the direction of the magnetic field, say the direction of the magnetic field, suppose at this point, what will be the direction of the magnetic field? We have to plot a tangent at that point. Okay, at this point, what will be the direction of the magnetic field? We have to draw a tangent at this point. Okay, so this is a current carrying wire and the circulation of the magnetic lines of force around the wire, and the direction of magnetic field at any point, you have to just plot a tangent at that point. Okay, so now what I am going to do, see, let me plot it again. So this will be the direction of the magnetic lines of force. Okay, and this send, whether it is anti-clockwise or clockwise, you will determine from that right hand thumb rule, which I have already mentioned. Just put the thumb along the direction of the current and curl your finger through that point, at which point you want to determine the magnetic field. So this direction will give you whether it is clockwise or anti-clockwise. Okay, put your thumb like that and curl the finger. Okay, so this is the sense whether it is clockwise and anti-clockwise. It will determine by this curling of curling your finger will give that direction. Okay, so now what I'm going to do, I'm going to put another conductor here. Two conductor, put it parallelly. Say this is a conductor and we put it parallelly. And say same current is flowing, current is flowing in the same direction. Okay, same current is flowing in the same direction. Okay, so suppose now this conductor will be in the region of the magnetic field created by this lower conductor. Say this is lower conductor and this is upper conductor. Okay, so upper conductor will be in a region of the magnetic field created by this lower conductor. Okay, and the direction of the magnetic field, the current is flowing in that direction. Therefore, it's suppose if we consider a length dl, or length L of the conductor, its direction will be along this direction. Okay, and the magnetic field at the point where L is located, we have to just draw a tangent at this point. Okay, so this is the magnetic field. Okay, and this magnetic field will be always perpendicular to the length L, because you see this is a circle. If we plot any circle, suppose this is a circle, the length is like that, and and suppose this is a tangent and the length is like that. Okay, so the tangent to any circle is perpendicular to this line. Okay, therefore the length vector will be always perpendicular to the magnetic field vector. Okay, and this magnetic field is created by the lower conducting wire, that you have to remember. Okay, the magnetic field is always perpendicular to that length vector of the upper conducting wire. Okay, so in the previous classes I have discussed if a current carrying wire of length L is placed in a magnetic field, what is it will basically going to experience as a force. Okay, in this case the upper current carrying wire is carrying a current I, and it is region of magnetic field created by the lower conducting wire, and the value of the magnetic field is B lower. Okay, and the length vector of the upper conducting wire is perpendicular to the magnetic field created by the lower conducting wire. Okay, so if we consider the force on the upper current carrying conductor, in this case that value will be F upper, okay, I into L cross B vector. Okay, that I have already discussed many times. Okay, and here L and B are perpendicular to each other, therefore this value will be equal to I L cross B vector L B into sine 90 degree, because L and B are perpendicular into n cap. Okay, so I B into L. Okay, here B is equal to B lower, right? B lower, and L is upper length, upper wire we have considering. So L is upper and B is the lower. Okay, I hope you understand the meaning of this suffix. L upper means we are considering the upper conductor, and it is in the region of magnetic field created by the lower conducting wire, so we are doing it at B lower, and the current carried by this upper conducting wire is I. Okay, so this will be n cap. I B lower, L upper into n cap. Okay, now what we are going to do, we are going to determine the value of the the direction of the force, whether which direction the force is acting. Okay, this force is on the upper wire due to the current flowing in the lower wire. Okay, so as you can see, if the length vector is say in the x direction, okay, and B vector is perpendicular, say it is in the y direction, then the force will be along the z direction. The force will be along this. Okay, suppose if we are considering it as x direction, B lower is will considering as y direction, then the force will be along the z direction. Okay, so at each point of this conductor there will be a force due to the magnetic field created by the lower conductor, which will be along this direction. If we consider this as the z direction, so this is the z direction. Okay, now from the figure, as you can see, the force is towards the lower conducting wire. Okay, so therefore we can see the upper wire feel a kind of attraction towards the lower wire. Okay, because the force is directed towards the lower wire. If the force is directed opposite to the wire, then the upper, we will say that upper conductor is experiencing a little kind of repulsion from that wire. But since the okay, now if we put the value of B lower in this expression, then let's see what we'll get. If you remember from the last lecture, the magnetic field due to a infinite current carrying conductor mu naught into I divided by twice pi into R. I mean R can be X, Y, Z, anything. Therefore, I have put it as a R. Okay, so we don't have to. We have much more liberty than choosing X, Y, or Z axis. Okay, so for the time being, let's say the difference between these two wire is equal to R. Okay, the distance between the upper and the lower wire is R. Okay, so if we input this value, I B lower is equal to mu naught into I divided by twice phi into R. L, length of the upper conductor, say this is L, into the length of the upper conductor, and this is in the Z direction, so N cap will be Z. Okay, F upper. Okay, so this is the force which the upper wire will experience if it is placed in a magnetic field due to the current I in the lower wire. Okay, so to make a distinction between these two current, let's put this is I1 and this is I2. Okay, so in this case, this I will be equal to I2, this I will be equal to I2, and say this will be I2. Okay, and this I will be I1, because this is the, and this magnetic field is due to the current I1. So this is I1. Okay, so now the distinction is clear between I1 and I2. Okay, so this is the magnitude of the force mu naught I1 I2 divided by twice pi R into L, and its direction is towards the lower wire. Okay, so if we put the magnitude of the force per unit length of the wire, now I am taking the magnitude. Okay, we don't have to worry about the direction because we already know what is the direction. Okay, so F by L will be equal to mu naught I1 into I2 divided by twice pi into R. This is the force per unit length. Per unit length of the upper wire, it will experience this kind of a force. Okay, towards the lower wire. Sorry. Similarly, the same logic also applies to the lower wire also. The lower wire is also in a magnetic field created by the current I2, because current I2 in the upper wire is also going to produce its magnetic field, is not it? And the lower wire will be in this magnetic field. Therefore, the lower wire will experience a force along upward direction. Okay, this will be only in the upward direction if the direction of current in the two wire are in the same direction. Okay, if it is in opposite direction, the force will be repulsive. The direction of the force will be towards this direction, Okay, so that thing you have to remember. Okay, so one can say that if two conductor carrying a current in equal direction, then the two wire will attract each other. So basically in the book you will find that the parallel current attracts each other. Okay, here see, parallel means current in the same direction. I1 is in this direction, I2 is also in this direction. Okay, and if in case if I1 and I2 are in opposite direction, say I2 is along this direction, I1 is along this direction. Okay, in that case there will be a force of repulsion. Okay, and the force per unit area exactly will be same. F by L always will be mu naught I1 I2 over twice pi R. Okay, so I hope it's clear. The upper wire, for this scenario, the upper wire will feel an attraction towards the lower wire, and the force per unit length of that attraction will be mu naught I1 I2 divided by twice pi R. Similarly, the lower wire also feel similar kind of force on the upper wire, and its value will be also, say this is upper, and lower wire also F lower divide per unit length. If L is the length of the wire, that will be equal to mu naught I1 I2 divided by twice pi R. We also assume that the length of the two wire are also same. Upper wire length is also L and lower wire length is also M. Therefore, we have found that F by L is equal to mu naught I1 I2 divided by twice pi R. This is the most basic definition between the force between two parallel current carrying conductor. Okay, and this force is attractive. And if the direction of current is opposite to each other, that means if it is anti-parallel, then the both wire will repel each other. You can see it. You can just do the vector diagram and see. You can always see that when the direction of current changes, there will be a force of repulsion between these two current. Okay, so this is good. So far it's good. Okay, now from here we can define the definition of ampere. Suppose in both the wire, through both the wire, 1 ampere current is flowing. Okay, then let's see, let's put the value of 1 ampere, I1, for I1 let's put 1 ampere, and I2 let's put 1 ampere, and let's keep the two wire at a distance of 1 meter. Okay, so what I mean is that I1 is equal to 1 ampere, I2 is equal to 1 ampere, and let's also the distance is 1 meter. Okay, and then put all this value and see what is the force per unit length on the wire. Okay. In this case, what we will find that the force per unit length F by L is equal to mu naught divided by 2 pi. Okay, I1 1 ampere, I2 1 ampere, and length is, distance between them is also 1 meter. Therefore, force per unit length is equal to mu naught divided by 4 pi. Okay, and mu naught divided by 4 pi has a value of 10 to the power minus 7. Therefore, mu naught divided by 2 pi will have a value of 2 into 10 to the power minus 7. Okay, so this value will give us 2 into 10 to the power minus 7 F by L. F is Newton and L is meter. So its unit will be Newton per meter. Therefore, F by L is equal to 2 into 10 to the power minus 7 Newton per meter. Okay, so from here we can give the definition of ampere. Definition of ampere. So from here, as you can see, what will be the definition of ampere? That 1 ampere is that much of current if it flows through two conducting wire which are parallel to each other at a distance 1 meter apart. Then the force of attraction between the two wire is 2 into 10 to the power 7 Newton per meter. Okay, so this is the definition of ampere. So I repeat again, 1 ampere is that current if present in each of the two parallel conductor of infinite length and 1 meter apart in empty space, then causes each conductor to experiences a force exactly equal to 10 to the power 2 into 10 to the power minus 7 Newton per meter. So this is the most basic definition of ampere. Okay, so let me write it again for your understanding. Let me write it. Okay. 1 ampere is that much current, that much unvarying current, because I am not considering the case of time varying current. It's a DC current. Okay, so it means unvarying current when flows in two parallel conductor. Parallel conductor means current in the same direction. 1 ampere is that much unvarying current when flows in two parallel conductor. The force experienced by per unit length of the conductor is 2 into 10 to the power minus 7 Newton per meter. And this is, and it's the force of attraction, and it's the force of attraction. Okay, so this is the most practical definition of ampere. Or one can also say that if 1 ampere is that much unvarying current when flows into anti-parallel conductor. Anti-parallel means the current in one conductor is opposite to the current in another conductor. So in that case, the force per unit length experienced by the two conductor will be 2 into 10 to the power minus 7 Newton per meter. So that is also an alternative definition of an ampere. Okay, so ampere you can define with respect to attractive force and with respect to repulsive force also. Okay, so from this discussion we know that the parallel current, they attract each other, because this is already we have proved using F is equal to I into L cross B definition, and also from this part we have also managed to get the definition of 1 ampere. Okay, so hope you have understood this topic, and in the next part I will discuss about the magnetic field due to a current carrying loop. Okay, due to a current carrying ring or a loop. Okay, so thank you.